we have solved linear programming problems by graphical method. This method is useful when there are not more than two variables and the number of constraints is less, as it is easier to deal with two-dimensional graphs. All the feasible solutions lie within the feasible area for the optimal solution. However, if we've got large number of variables or constraints, it is still true that the optimal solution would be found at the vertex of a set of feasible solutions. In fact, we would find these vertices by writing all the equations corresponding to the inequalities of the set of problems and then proceed to solve all possible combinations of these equations. Then we could evaluate the objective function at the feasible solutions. After all this, we might discover that the problem has no optimal solution at all. Therefore, this method would be highly cumbersome and time consuming. Suppose there are 4 variables and 7 constraints. We could have to solve all possible combinations of 4 equations chosen from a set of 7 equations. Obviously, there would be 7C4 or 35 solutions in all. Each of these solutions will then have to be tested for their feasibility. So even for this relatively small number of variables and constraints, the work would be quite tedious. One very efficient technique of solving these kinds of optimization problems with large number of variables and constraints is given by Simplex method. The Simplex method or Simplex algorithm is matrix-based method used for solving linear programming problems with any number of variables. It is a method developed by George B. Dantzig, an American mathematician, in 1947. The Simplex method is an iterative procedure, solving a system of linear equations in each of its steps and stopping when either the optimum is reached or the solution proves infeasible. After studying this module, you shall be able to understand Simplex method, when to use Simplex method, define slack variables, prepare the linear programming problems in order to solve it by pivoting using the Simplex method, solve the linear programming problems using Simplex method. Let us now first understand the solution of linear programming problems by Simplex method. The procedure for solving the given problem is illustrated with the help of an example in the following steps. Step 1. Standard form of a maximum problem. A linear programming problem is in the standard form if it seeks to maximize the objective function z is equal to c1x1 plus c2x2 plus going till cnxn, subject to the constraints a11x1 plus a12x2 plus going till a1nxn less than equal to b1 and a21x1 plus a22x2 plus going till a2nxn less than equal to b2, the solutions going till am1x1 plus am2x2 going till amnxn less than equal to bm. The conditions required for a linear programming problem to be in a standard form are: first, all the variables are non-negative, that is, xi's are all greater than equal to 0. All the constraints and objective function, which is to be optimized, are written as a linear expression. Also note that for a linear programming problem in standard form, the objective function is to be maximized and not minimized. The right hand side of the constraints is positive or equal to 0, that is, bi is greater than equal to 0. If the right hand side of the constraints are negative, then it must be made positive by multiplying both the sides of the equation by -1. Example, suppose we want to find the maximum value of p is equal to 6x plus 5y plus 4z, where all 3x, y, z are greater than equal to 0. Subject to the following constraints: 2x plus y plus z is less than equal to 180. X plus 3y plus 2z is less than equal to 300. And 2x plus y plus 2z is less than equal to 240. Let us check whether the problem is in the standard form or not. This is a maximization problem containing two variables, x, y and z are non-negative. If the objective function is a minimization problem, we have to convert it to max minus p. The objective function and constraints are each written as linear expressions. bi is less than or equal to a positive constant. Therefore, we conclude that the maximum problem is in the standard form. Adding slack variables. In order to solve the maximum problem by simplex method, we need to convert the inequality constraints into equalities by adding slack variables. Since the left-hand side of each inequality is less than or equal to the right-hand side, there must exist non-negative numbers that can be added to the left-hand side of each equation to produce the following system of linear equations. These numbers are called as slack variables because they take up the slack in each inequality. These slack variables are introduced since it is easier to deal with equalities than inequalities in mathematical treatment. Example, in order to take up the slack between the left and the right sides of the constraints, let us introduce the slack variables S1, S2 and S3 which are greater than or equal to 0 such that the following structural constraints will be converted into following inequalities. 2x plus y plus z plus s1 is now equal to 180. X plus 3y plus 2z plus s2 is equal to 300. And 2x plus y plus 2z plus s3 is equal to 240, where x, y, z, s1, s2 and s3 are all greater than equal to 0. The objective function becomes minus 6x minus 5y minus 4z plus 0s1 plus 0s2 plus 0s3 plus p is equal to 0. The slack variables will always be non-negative, 0 or positive when solving linear programming problems. Forming a simplex table. The last row depicts the objective function. Equations are solved in terms of non-basic variables x, y and z. The variables that appear in one equation only are called basic variables except p. Here s1, s2 and s3 are all basic variables. A basic solution of a linear programming problem in standard form is calculated by setting non-basic variables equal to 0. So, basic feasible solution would be x is equal to y is equal to z is equal to 0, implying that s1 is equal to 180, s2 is equal to 300, s3 is equal to 240 and p is equal to 0. We get this by solving the objective function and constraints. As long as there are negative numbers in the objective function, the solution is not feasible. Thus, we pivot the table to find the feasible solution. Pivoting the simplex table. What is pivoting? Pivoting means to pivot a matrix about a given element called the pivot element is to apply row operation so that the pivot element is replaced by 1 and all entries in the same column called the pivot column becomes 0. More specifically, in the pivot row, divide each entry by the pivot element, we assume it to be not 0, obtain 0 elsewhere in the pivot column by performing row operations. How is the pivot element selected? First, we find the pivot element. The column with the highest negative number in the objective function is chosen, which is column 1 here, as the highest negative number is minus 6. Divide each constant to the right hand side of the bar with the corresponding non-zero element in the pivot column. For example, 180 divided by 2 gives you 90. 300 divided by 1 gives you 300 and 240 divided by 2 gives you 120. Let us understand how to apply smallest quotient rule. Select the smallest quotient. The pivot element is the intersection of the column with the most negative indicator and the row with the smallest quotient. The pivot is the 2 in the column 1 in this table. Now change the pivot element to 1. We can do this by R1 is equal to half R1 as a row operation. Now we pivot about the pivot element to make other elements in the column equal to 0. For this, R2 equals minus R1 plus R2, R3 equals minus 2R1 plus R3, R4 equals 6R1 plus R4. When pivoting is done and we set the non-basic variables to 0, we obtain a solution called as basic feasible solution to the linear programming problem. The basic feasible solution from the tableau is x is equal to 90, s2 is equal to 210, s3 is equal to 60 and y is equal to 0. Z is equal to 0, s1 is equal to 0 and p is equal to 540. However, even this is not optimal as there are negative elements in last row. If a negative indicator is still present, we keep on pivoting. On the other hand, if no negative indicator is present, the maximum of the objective function has been reached. Pivoting again. Determine a new pivot element. Select the column with the most negative indicator. It is column 2 in this table. Divide each constant to the right of the bar by corresponding non-zero element in the pivot column. For example, 90 divided by half is equal to 180 and 210 divided by 2.5 is equal to 84. Select the smallest quotient, which is 84. The pivot element is in the intersection of column with the most negative indicator and the row with the smallest quotient. The pivot is in the 2.5 column 2 for this table. Now change the pivot element to 1. We can do this by row operation. R2 is equal to R2 divided by 2.5. Now we pivot about the pivot element to make other elements in the column equal to 0. With row operations, R1 is equal to minus 0.5 R2 plus R1. R4 is equal to twice of R2 plus R4. Since there are no negative indicators in the last row, the objective function has been maximized. The basic feasible solution from this tableau is x is equal to 48, y is equal to 84, s3 is equal to 60, z is equal to 0, s1 is equal to 0, s2 is equal to 0 and p is equal to 708. We do not have to mention the slack variables as they are not part of this final solution, but just as a tool to help us solve the problem. We shall now understand the flowchart explaining the simplex method. The simplex algorithm flowchart starts with insert slack variables and find slack equations, then rewrite the objective function and put it below the slack equation, then write the initial simplex tableau, find the pivot element by finding the most negative indicator in the last row and using the smallest quotient rule for the row. Perform the pivot operation. Are there any more negative indicators in the last row? If yes, go back to pivoting. If no, the maximum has been reached. Let us summarize what we have learnt so far. We have learnt, firstly, to use simplex method to find the optimal solution of a linear programming problem when the given problem has a large number of either variables or constraints. Prepare the linear programming problem in the problem for standard form to solve it by pivoting using simplex method, to introduce slack variables on the left side of each inequality from an equality, to write the initial simplex table, and to solve the linear programming problems using the simplex method.